Welcome back everybody. This is our 7th class in JEE Mains previous year question series, 4th chapter moving class and magnetism. Before this video, in this series we have made 6 videos related to this chapter and all of those are available on our YouTube channel. We have also started similar series for NEET previous years. So you can, if you have some friends who are preparing for NEET, then you can guide them to that playlist also, and both of these playlists are available on our YouTube channel in the playlist section, and name of channel is Point Basics. Now if you like these videos, then you can press the like button, share them and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount, however it may be, small it may be or whatever it may be, will be highly appreciated. Now with this, let's start today's video, and I think we are around somewhere 50, question mark number 50. So this was the last which we covered, 48, and today we will cover the 49th. So let me adjust pen thickness and let's start. A Helmholtz coil has a pair of loops, each with n turns and radius r. So these are two loops, each having n turns and radius r. They are placed coaxially at the distance r, and the same current flow through the loops in the same direction. Magnitude of magnetic field at P, midway between the point centers A and C. So it is mentioned that they are placed coaxially. So here from this diagram, it is not clear that how they are placed. They are placed coaxially. So let me draw a different diagram so that it can become clear that they are placed coaxially. Suppose this is our first loop, and let's copy it, and here we will have second loop. This is our second loop, and they are placed coaxially means their center coincides with each other. Something like this. So there is, let's name the points as per mentioned, that this is point A, this is point C, and there is some point midway, in the midway between these two, that is P. Their distance is r, so distance mentioned is r. This distance is r, and their radius is also r. So this distance is also r, and we have to find this distance also. So let also mark this one in for the reference. So let's mark some point. This is A, C, we have P. So suppose this is B, this is T. So AP is equal to, as distance between A and C is R, so AP is equal to R by 2, and AD is equal to R. So this distance PD will be equal to PB, because the diagram is symmetric, and it will be r square plus r square by 4. So 5r square by 4 under root, or root 5r by 2. This will be the value of PD. Now coming to the one of the loops. As mentioned, that current in both of these is in same direction. So suppose current is here something like this. In this loop, and in this loop also current will be something like this. Now let's find out magnetic field at P, magnetic field at P due to this first coil which has a center at A. We know for a coil, or we can say a magnetic field due to ring, we know, then we can just multiply it by number of turn it has, so we get the magnetic field due to coil, and it will be, so magnetic field due to coil uh, A, it will be mu node n, where n is the number of turns, I is the current, now times r square, where r square is its radius, divided by this distance PD power 3 by 2, or I can say, oh sorry, not 3 by 2, square of this distance, that will be, square of this distance will be 5r square by 4, now raised to power 3 by 2, and we have 2 also here. Now this is the value of magnetic field due to this coil at point P. Similarly, due to this coil, there will be a magnetic field at point B, at point P, and its value will be same because both of these coils are identical. So mu node n I r square divided by 2 5r square by 4 power 3 by 2. Now the important thing that is here, we have to find out the direction of the fields, that what will be the direction of the magnetic field, and either they will be added or they will be getting subtracted, or they will be at some angle to each other. Now let's first come to this coil. Suppose you are a person who is sitting here. You are a person and who is here in the midway. So according to you, what you can see, that this coil, or we can say, let's change your position so that we can observe both of the coils simultaneously. We are out of the coil system, and you see that in this coil, according to you, current is anti-clockwise. We are assuming here that if you are looking from this side, you are in the left of the coil, and this side is upper side of the coil, means this side is in front of the screen and this is in the behind of the screen. So according to you, this current will be flowing in anti-clockwise direction. And if it is anti-clockwise direction, we know anti-clockwise direction, we can make north pole out of anti-clockwise direction, because we know that we have already discussed that how to make poles, that we can make north pole something like this. If we have anti-clockwise rotation of current, then it represents north pole, and if we have clockwise orientation of current, then it represents south pole. So for this coil, you have north pole here and south pole here, and similarly, for as direction is same, we have north pole here and south pole here for this, we can say, both of these coils. Now we know that magnetic field lines emerges from the north pole and at south pole outside, and inside they travel from south to north. Outside they travel north to south, and inside north to south. So we are just taking as this point here. So for this coil, field will be something like this in the negative x direction, and for this coil also, field will be in the negative x direction. So we can say at point P, both of fields are in negative x direction, so both of fields will get added. Hence total field at point P will be sum of these two fields, and we can just simply write it twice, mu node n I r square divided by twice of, now square root will be 5r by 2 power cube, 2 get cancelled, and we will have mu node n I r square divided by cube of these, so it will be 5 root 5, and cube of 2 will be 8, and it will go up into r cube. So we will have 8 by 5 raised to power we can say half 3 by 2, because here we have half power of 5 and here we have 3 power, so 3 by 2, and this r square get cancelled, mu node ni divided by r. So I think this one matches out. Option B will be the right answer. Moving to the next one. A current of 1 ampere is flowing on the sides of an equilateral triangle of side length is given. Magnetic field at the center of the triangle will be. So we have already solved question like this, and I think it was question number 43 or something. Let me find out. Yes, this was the question, that magnitude of magnetic field at the center of equilateral triangle with loop side 1 meter. In this one, we had a side length of 1 meter and current value 10 ampere. In the right question which we are doing right now, question number 50, in that side length is changed and value of current is changed. So here how we solved it, we found out the value of current of magnetic field due to one of the side, and then we multiplied it by 3, and we can see from here that this value can be reduced to, it will becomes BAC is equal to mu node I by 4 pi d, as these angle will stay the same. However, we can say whatever will be the side length, angles will stay same, so sine phi will stay same. From this we will get 2 root 3, twice of root 3, oh, sorry, not twice of root 3, we get root 3, we get only root 3. So this will be the value of we can say magnetic field due to one conductor, and as there are total 3 conductors, so it will be multiplied 3. So mu node I 3 root 3 by 4 pi d will be the answer. Now let's variables here, or let's copy this formula and put all the variables for the question which we are solving. Copy. Now paste it. So this will be the final value of magnetic field. Now mu node by 4 pi is 10 raised to power minus 7. Current is 1 ampere into 3 root 3 divided by distance d. Now we have to find out that distance d, and let's again go to the previous question. There we have also solved for distance d. And here it is, that in this triangle, here triangle OAD, triangle where is OAD, in this triangle OD by DA, that was half of the side length. So we can say OD by half of the side length was equal to tangent 30, angle will stay the same, is equal to root 3. So OD, that is perpendicular distance, is equal to A by twice of root 3. So we will use this value here. So D is equal to A by twice of root 3. Putting this value here, 10 raised to power minus 7, 3 root 3. Value of side length is 4.5 into 10 raised to power minus 2 divided by 2 root 3. So 2 root 3 will go here. And finally, we have root 3 into root 3, 3. 6 into 3, we will have 18 divided by 4.5 into 10 raised to power minus 5. And we can further write it like this, that it will be 180 by 45 into 10 raised to power minus 5. We can cut both of these on 9. So 20 and 5 and 4. So 4 into 10 raised to power minus 5 will be the right answer. Option A is the right answer here. Moving to the next one. Two identical wires A and B, each of length L, carrying same current I. The wire A is bent into circle of radius R, wire B bent into square of radius A. If B, A and B are the values of magnetic field at the center of the circle and square respectively, then BA by BB will be. So we have to solve for, we can say, their magnetic field, individual magnetic fields. So let's slide it down slightly and draw a line here. Because we know for the circle we can easily find out. We have already have the formula. For the square we have to find out. Now for circle, and here we will solve for square. Now as length is same, current is same, so when we make a circle of, we can say, radius R out of wire of length L, then circumference of that circle should be equal to length of the wire. So from here, radius of circle comes out to L by 2 pi, and now we know magnetic field at the center of a loop or a ring, that is mu node I by twice of R. So mu node I by twice of L by pi means L, and we will have pi here. So this is the magnetic field due to circle, and that is denoted by A. So we will write here BA. Now going to square. For square, if it has a side of A, then its circumference or its perimeter should equal to total length L. So L is equal to 4 times A, and from this A comes out to be L by 4. Now let's draw a square. Suppose this is our square. And here again we will use magnetic field due to a straight conductor. Now suppose this is its center. So as mentioned, this distance is A. So if we draw some lines here, so that we can find angles to use in the formula for the straight conductor. So suppose this is the first one, second and third, and let's name them O, A, B, C. This will be the angle phi 1 and this will be the angle phi 2, and we know that AC is equal to side length A, so AB will be half of that, so AB will be A by 2, and OA, the value of OA we can also find, or we can say OB. Again, OB is also A by 2. OB is also A by 2 because this whole length is equal to CD, that is OB is half of CD and CD is equal to side of square, that is A. So using these two, we have AB and we have OB, we can find out that tangent phi 1 or value of phi 1, as both sides are equal, so angle will be 45. So again phi 1 is equal to phi 2 is equal to 45 degree. So magnetic field due to AC part, magnetic field due to AC part will be mu node I divided by 4 pi into distance, that distance is BO, that is equal to A by 2. So and A is equal to L by 4. So we can say A by 2 will be L by 8. So L by 8. Here sin phi 1 plus sin phi 2, sin 45 is 1 by root 2 plus 1 by root 2. And from this we have 2 here. So this magnetic field comes out to be 2 mu naught I divided by pi L, and we will have here 1 plus 1 2 by root 2, so root 2. Now this is due to one conductor. We have similar 4 conductors, and magnetic field of all of these will be added at the center. So total magnetic field for square, that is B2, will be 4 times of this value. So it will be 8 root 2 mu naught I divided by pi L. So now we can divide both of these, or it is, I think, B denoted by B. So BA by BB will be mu naught I pi L divided by 8 root 2 mu naught I pi L. Mu naught I cancelled, L get cancelled, so we have pi square by 8 root 2. So option B will be the right answer here. Moving to the next question. Two long current carrying thin wires, both with current I, are held by insulating threads of length L, are in equilibrium as shown in the figure. The threads making angle theta with the vertical. If the wires have mass lambda per unit length, then the value of I. So we have to find out value of current, and these are the wires which we are talking about and which have mass per unit length lambda. So we have to find out the value of current in the terms of lambda and all that stuff. So let's slide it slightly. Now assume both of these wires, as mentioned, that they have current in the same direction, I think. And we know that if we have two conductors, and if they have current in the same direction, then what happens? They start attracting each other. So if current in both of these wires is in same direction, then they will attract each other and they will start touching, they will come in contact with each other. And that's not the case here. Here they are at some they are in equilibrium at some distance. It means that current in both wires is in opposite direction. We assume that magnitude of the current is same, but their direction is opposite. So they are exerting repelling force on each other. Now let's come to the, we can say, free body diagram for both of these, or at least one of these. So let's draw. Say, let's choose red color. So their mass will act downward. This will be the tension. Here we'll have T cos theta. This will be T sin theta. And we will also have a magnetic force, a repulsive magnetic force. So this is mg. This is T sin theta. This is tension, because this is theta and this is also theta. So this will be theta. And this is T cos theta. And here we have magnetic repulsive force. So we can write that T cos theta is equal to mg and T sin theta is equal to we can magnetic repulsive force. And from these two we can divide both of these to find out, we can say, tangent theta will be F P by mg. Now first of all, let's find out this Fp, the repulsive force. We know that when we have two parallel conductors, then their repulsive force is given by, so force between either attractive or repulsive between two conductors, and this is actually force per unit length, not force per unit length, either attractive or repulsive between two conductors is given by mu naught by 2 pi 2 into I1 I2, where I1 and I2 are the currents of these two conductors. In this scenario, we have we can say current is same, and the value of d is the distance between these two conductors, that we can write that as this is d. So if I mark a line here, suppose AB, and this is O, so OB is equal to L, we have an angle theta here, then AB is equal to L sine theta. So AB is equal to L sine theta, and distance between these two conductors is twice of the AB, so the value of D is twice of the L sine theta. So from this we can write that F is equal to mu naught by 2 pi, distance between them is 2L sine theta, current is same, so I square multiply by L, that L comes here. That's how we get the value of FB, and L get cancelled here, so it comes out to be mu naught I square by 4 pi of sine theta. That's the, we can say, magnetic force. Now we can put this value here, so we will get tan theta is equal to mu naught I square by 4 pi sine theta into mg. And as we can see from the options, none of these options list mass. In none of these options we have mass. So I think so we have to substitute this mass, and that can be done from here, that if wires have lambda mass per unit length, then the value of I. So it is given that mass per unit length is lambda. So if mass per unit length is lambda, and we are taking length L here, we are taking length L, then total mass will be lambda times L. So mg is equal to lambda L. Then we can substitute this value here. So tangent theta mu naught I square 4 pi sine theta into lambda L, and we have to find value of I. So what we do, we will exchange these terms. So I square will be 4 pi sine theta lambda into tangent theta by mu naught, and we can further solve it like that. I will be tangent theta, we can use at sine theta by cos theta, so sine square, sine will be out of the under root, sine theta under root pi, and I think 2 sine theta, because 4 will be again out of under root, so 2 sine theta pi lambda, and what we have extra, we have L also, L also, so pi lambda L divided by mu naught, and from this tangent theta, that was sine by cos, we have cos theta also. So if now we match the options, we have 2 sine theta pi lambda L, we have mu naught cos theta, we are missing L, and I think we made a mistake in the substitution of mg. Okay, yes, lambda L is the mass per lambda is the mass per unit length, not the weight. So m is equal to lambda L and mg is equal to lambda Lg. So we have g here additional. So g will be here, g will be here, and g will be here also. So option D will be the right answer. Here some of you can be in doubt regarding the length, that in the question it is mentioned that capital L is the length of the thread but not the length of the conductor. Then why we have chosen as L as the length of the conductor also? Now, because when calculating distance between them, the distance between them was 2L sine theta. Here it is. The distance between them 2L sine theta, and here I'm using capital L and smaller l as similarly. So assuming that small l is the distance, is the length of the thread, and 2L sine theta is the distance between them. Here we assume that, let us consider that L is the length of the conductor. Here I assume that L is the length of the conductor. So it is my assumption so that I can solve the question. If I have been assumed that there is some other length, suppose x, then there might be some difference in the answer and our answer will not match as per these questions. In these questions, it's by default assumed that if one length is given, then another length will be taken in the similar manner. So that's why as per question, the length of the thread is L, and we are also taking same length for the length of these conductors. Okay. So with this, let's move to the another one. Consider two thin identical conducting wires covered with very thin insulating material. One of these wire is bent to form a loop, produce magnetic field B1, and at the center when a current I passes through it. So, and second, I think it is not mentioned. So here statement is not clear that what is the second one which is mentioned here. That first one we made it into loop, and second one we don't know. So there is problem with statement of this question. Let's move to the next one.